Hello everyone, welcome back to another IB Chemistry 2025 specification video. Today will be a HL only reactivity video in which we will be working with Hess's law. So let's start with where this came from to better understand what its uses are. So, one of the first laws of thermodynamics, the law of conservation of energy, states that energy cannot be created or destroyed, but it can change form. And this means that within a closed system, the total energy present will always be constant. Now, a closed system is a system in which neither products or reactants leave the system, meaning that the total heat will always be contained within it, hence the energy present always being constant. So Hess's law can be used to calculate the standard enthalpy change of a reaction from known standard enthalpy changes. These standard enthalpy changes, their values will be given to you in a data booklet in your exam, and these will show the standard enthalpies of formation for all of the bonds that you will need to have access to in your exam. So Hess's law states that the total enthalpy change in a reaction is independent of the route by which the chemical reaction takes place, as long as the initial and final conditions stay the same, or if it's all undergone its reactions in standard conditions, for example, same pressure, same temperature. So let's get to actually getting out the equation. So Hess's law and his equation states that the change in enthalpy is equal to the sum change of enthalpy of products minus the sum change in enthalpy of reactants. So in reality, when we see this, it looks quite simple, but this can get quite complicated in our energy cycles. So let's start with the standard enthalpy change of formation. And let's do that right under our square. So the standard enthalpy change of formation is the change in enthalpy when 1 mole of product is produced from elements in standard states and conditions. And these will be 298 Kelvin and 10 to the power of 5 pascals. Next up, let's have a little example to better understand what this looks like. So let's say we are forming ethanol. So 2 carbons, 6 hydrogens, and half that oxygen will give us C2H6O. And as we see, we have 1 mole of our product. So the standard enthalpy of formation here would simply be that of all of these reactants summed. Next up, we have our standard enthalpy of combustion. And let's make some room for this. standard enthalpy of combustion is a little bit different, because standard enthalpy of combustion is the change in enthalpy of 1 mole completely reacting with oxygen at standard conditions. So it'll be 1 mole of a fuel, for example. So let's draw ourselves a nice energy cycle to visualize this, because it gets a bit more complicated now. So here we have the combustion of methane gas, and we have ourselves a little energy cycle. So what we want to find is the change in enthalpy from our products, our reactants, to our products. Apologies. And down here we have the constituent elements of these products and reactants. So with these arrows, Hess's law states that the direction, in a sense, of a reaction will always be from something's constituent elements to its products, which means that these little arrows, as I drew, will be going up towards our carbon dioxide and fuel and so on and so forth. So to calculate the change in enthalpy here, we need to essentially follow the path. So here we have change, let's call it change 1, and then we have change 2. So to find, let's call that change total over there, just a bit of math. So change in enthalpy total will be equal to change in enthalpy 2 minus change in enthalpy 1. And that's because we are going against this arrow, making this value have to be subtracted instead of added on. And this path that we are taking here, let's take a new color, a different one, from here to here to here, and that one up there, they are the same because, as we stated, within our closed system, the total energy present will always stay the same because neither reactants nor products will be lost to the universe. And that is why Hess's law works, because we are under the assumption that standard conditions are where we will find our reactants and our products, and this will be used when calorimetry cannot be used to calculate changes of enthalpy because certain reactions may not occur under standard conditions. So if we were to take, I've pre-calculated these values, so this over here is negative 965, and this would be negative 75, but double negative gives us a positive. Therefore, the total change in enthalpy is of minus 890 kilojoules per mole. Now that's one example of what it looks like when you draw out an energy cycle. These are very useful for you to understand the direction in which a reaction is occurring, so you know which changes in enthalpy can stay as given in terms of negative or positive as they're given in the data booklet, and which ones you'll need to flip around due to the direction of these little arrows over here. They're very useful and make this much easier to understand. Let's just take another little example in which we do not have constituent elements at the bottom, but as our reactants, as we did down here before I had to erase them for a standard enthalpy of formation. So let's do another combustion one. So we will have 2 carbons with 3 of those, and have that, the same thing that we had earlier, giving us C2H5OH. So broken down, or in better words, we know that the route that this reaction will take, first of all, our carbons will be oxygenized, so we know that this will form carbon dioxide, even though down here we have 2 oxygens and up there we only have 1. Do not worry, that is simply the way that this is done. Since it's a combustion reaction, we know that carbon dioxide and water will be formed. And as we have elements as our reactants and not as something that our reactants will break down into before forming our products, our arrows will now go up. So reminder that this path over here is the same as this path over here, which is the path that we will be taking to calculate our standard enthalpy of combustion. So HT, that's T, this is 1, this is 2. HT will be equal to, apologies, these arrows are in the wrong direction because elements to compounds. So elements are above, we go down towards that part of the energy cycle. So HT will be equal to 1 minus 2, which will be, how much did we have? Well, in this case, it would be negative 273 kilojoules per mole. Really, it's not that hard to do the maths itself. The calculations are not complicated, but it's very easy to make a mistake in terms of which values should be positive, which ones should be negative, as I stated earlier, which ones need to be swapped around. Now, if we look at this, it may seem quite complicated, quite elaborate, much more complex than the formula that we have up here. But this really is just a simplified version of that, because we have our reactants over here and then our products over here. It's the same thing, it's just easier to understand what is considered the reactant and the product using this energy cycle diagram, especially as it kind of changes when we're looking at formation or combustion data. Now that is all that we need to know for this topic. Thank you for watching and hope that this was helpful.